Okay, so in this video I'm going to talk about quite a famous problem, and that's the problem of, well, I guess you can imagine, let's call it a limo and a garage. So you have some limo, and the limo is moving at some speed. Do I want to use a limo? Yeah, let's use a limo. And let's call the limo, well, we're going to need to use a few letters here. So let's call the length of this little l. But again, as soon as we introduce that, we have to consider the frame of reference. So in the frame of reference where this is moving, let's call it little l. So we know that's going to be length contracted. And then we have some garage in which we want to fit it. So there's some garage, some door here, and the garage has a certain length. And I'm drawing this from the perspective of the garage. So the garage is stationary, and I'm going to call this a length for, I'm going to use capital L here for that one, and I'm going to use a little subscript 0 just to indicate that's the proper length. So that's the length of the garage in the frame of reference where the difference in time between, say, that event and this event is 0. So when the temporal difference is 0, the spatial difference is known as the proper length. Yeah, that's a lovely way of saying it. And obviously you could look at this from the perspective of well, in this situation, you can imagine the car as being length contracted. So we could say, well, because the car is length contracted, and because it's moving, you can imagine how the car might fit in the garage in this situation because it is length contracted. But if you look at it from the perspective of from the limo's perspective, things change quite substantially. We have a length, let's call it little l, and then subscript 0 now. So that's the proper length in the frame of reference to the limo. And the garage is now the object which is moving. So what does that mean? It means it's going to be length contracted. So the garage is going to be length contracted. Let me now call this just big L. And this is now moving at a speed v, like that. So we know the relationship between these. So if you remember the length contraction, the big L it's the L0 and then divided by the gamma. So that, again, this is just the proper length. So remember, that's the length when you consider the temporal difference to be 0 in different reference frames. So this L here, this L, as I've wrote it, is it's the length when the temporal difference between that event and that event is 0. And likewise, this L0 is the spatial difference between when that event and that event, the temporal difference is 0. So again, you can imagine flashing light rays from these points and then synchronizing the clocks at this point and this point, and that would define the time at which you want to measure the proper length. But when you first look at it, you might say, hey, here it's the limo which is contracted and the garage which is proper length, and the proper length is longer than any kind of contracted length. So the garage, you might say the limo fits in the garage in this situation, but in this situation, the limo is a length of L0, whereas the garage is a length of L, which is now going to be length contracted. So the garage is shorter, the limo is longer. There's certainly a situation where the limo might not fit into the garage in this situation. Intuitively, or at least from like a first draft of thinking about this problem, that might be some of the conclusions you come up with. And you might say, hey, special relativity is broken, it's a load of rubbish, blah, blah, blah. Or maybe you just haven't thought about it well enough. Maybe you haven't considered the simultaneity of events and how significant that idea comes into play when you're considering these situations. So let's draw this space-time diagram for this, because again, to solve special relativity problems, the best way by far is to draw a diagram, think about the weld lines, and think about the transformation. So let's draw this picture here first. I'm going to need, so supposing little l is smaller than L naught in this situation. So let me draw that out. You have a big T here. So this is in the garage perspective. And then you have a big X like that. And the limo, well, he's moving at speed v, so he's going to, the beginning and the end of the limo is going to trace out weld lines. They're going to look about like this. It's going to be one weld line there. That's going to be the weld line of X equal v times time. And there's going to be another weld line here. That's going to be the weld line of X equal, and then VT, and then plus the length of the limo as measured from the garage frame, and that's what I was calling little l here without the zero. So the little zero means proper, and without the zero means contracted. So little l, that's going to be this length here in this frame of reference, and that would be little l there. So that's the limo's weld line. And it would continue into negative T as well. It's going to continue down here and also down here as well, like that. And then the garage weld line, well, again, you need to consider the beginning and the end of the garage. And in this perspective, it's quite simple. You have, the beginning of the garage is just going to be this weld line going up here. That's just the X equals 0. And then you have another weld line where the X is just equal to L. So maybe a bit like this. So if I call that big L there, sorry, big L naught, isn't it? Because I'm in the frame, or the reference frame where we're stationary with respect to that event and that event. So there's no temporal difference between that event and that event, and therefore the spatial difference is just L naught, and that's why it's the proper length. That's the proper length of the garage is L naught. And you can see in this frame, the limo is going to fit in the garage, right? You can see clearly how the little l is smaller than the L naught. But we now have to change this. We have to think about this from the perspective of the limo. So what does that look like? It's worth considering a few events here as well. So this is the weld line of the front of the limo, and this is the weld line of the rear of the limo. And so yeah, you can, I should have drawn this a bit bigger. Let me scale it up on another page. Let me copy that, go to the next page. It's the power of Photoshop. Right. Copy that in, scale it down a bit. Okay, there we go. All right, and this is going to be VT and then plus little l there. And then let's just scoot the axes down a bit, and then across a bit, and then down a bit. Okay, and I just wanted to continue that green line so we could think about the events and how they intersect and so on and so forth. So, I'm still going to miss it, aren't I? So there's going to be some event down here where the front of the limo enters the garage, and that's where the white line, or the red line as I was drawing it, would intersect the green line, the green weld line of the limo. So this is the front of the garage weld line. This is the back of the garage weld line. This right here is the front of the limo weld line. And this right here is the rear of the limo weld line. So you can see, as I've drawn this picture, I've drawn the rear of the limo passing through, well, just passing the front of the garage at time t equals 0. That's how I've set this up. And I want to draw, so we're going to have some events here. There's an event here, let's call that the event A perhaps. That's where the rear of the limo enters the garage. We have the event B here, that's where the front of the limo would hit the end of the garage. So that's where the front is going to crash into the back. And then we have some event down here. Let's call the event C down here. So imagine the intersection of the red line and the green line here. That's going to be where the front of the limo enters the garage. That's going to have some event C. And likewise up here, this green line, if you continue that green line all the way up and find the intersection of that with the red line, then let's call that the event D, somewhere up there, and C is somewhere down here. Then that's going to be the intersection of the back of the garage with the back of the limo, which hopefully wouldn't happen because the limo would kind of crumple as it crashes into the limo would begin crumpling at this point here when the front of the limo crashes into the rear of the garage. Anyway, so that's the events, and in this situation you can see how the event of B is behind the event of A. So in this situation, the event B precedes the event A, and the event B is the limo crashing into the back of the garage, and the event A is the back of the limo entering the garage. So event A is when the limo is fully within the garage, and you can see that happens before the limo crashes into the back of the garage. So in this situation, the limo is going to fit as I've drawn it. So that's all good. But and I guess that's the fuller picture. You have to consider the simultaneity of events. It has to be the case that event A precedes event B. If that wasn't the case, then if B was to precede A, then certainly the limo wouldn't fit in the garage. But at the moment we have A preceding B, so therefore the limo fits. Let's look at this from the perspective of the limo. So I might just do that on the same page here. So let me scoot over a bit, and let's just do it over here. So so this time I'm going to draw X prime stationary. This is the limo. And then you have T. Oh, this takes a bit forward, doesn't it? So T prime. It's going up there. Like that. And down. And this is now from the perspective of the limo. So that means the limo is going to have its own constant weld lines. And let's use the same colors again. So the limo was green. It's going to have a weld line going up there. T prime, X prime equals 0. That's going to be the same line as this one here. So that's the X equal VT line. And you're going to have another weld line where the limo, you have the front of the limo, like that. And that's going to be this distance L0 here. So this distance here is going to be L and then 0. So again, that's the proper length of the limo from the perspective of, that's the length of the limo. That's the spatial difference between the events, the front of the limo and the rear of the limo, when you consider those events to be simultaneous. So when the temporal difference is 0. And we now need the weld lines of the garage. Well, let's try and figure that one out. So what's it going to look like? It's going to be passing through the origin again. So it's going to be red line. And that's going to be kind of scooting backwards like this. If I could draw straight lines, a bit like that. So again, this is going to be the event A down here. Down here, that's where the front of the limo intersects the rear of the garage. So that's going to be the event C. That's where the limo starts entering the garage. So so this is the front of the garage. This is the front of the limo. So that's when the front of the limo starts entering the front of the garage. And what else do we have? We have this line here, X equals VT plus L. what's it going to look like here? Well, it's going to be, sorry, it's just the, no, this red line here is the x equals L naught. And that's going to look a bit like this. So in this situation, the the L naught would be longer than L. So this L naught is going to be greater than the L as I've drawn it over here. So I should have maybe drawn this line a bit wider. Let me just do that. So let's take that line out, and let me just draw it a bit fatter, a bit further away. So just to really exemplify the fact that this is the proper length of the limo, so it's going to be a bit longer in this frame of reference, like that. So that's going to be the L naught, like that. And then it may well be the case, it doesn't have to be, but it may well be the case that the weld line of the garage here actually precedes. So cool. What am I saying? I'm saying so that's the x prime axis, and this right here, that would just be the t prime axis there. So this is the t prime axis going up along that line. So that's just this line here, and then the x prime, well, you can see it intersects the green line right here. So that event there is going to be this event right here. And that's going to have some time. T as well as, well, the time, the t prime would be 0 for that coordinate, and the t prime would be 0 for this coordinate. So let's try and draw that on. T prime equals 0. Yeah, okay, so this is where things get a little bit tricky. So well, I guess we can think about it like this. The L naught is going to be the in this frame of reference, the limo is going to be contracted to L naught divided gamma, and I'm going to call that a length of L, and it may well be the case that's shorter than the proper length. So let me draw that in this picture. It may well be the case it looks a bit like this, like that. So the distance from here to here is the length as measured in this frame of reference, and that would be what I'm calling big L, and that's going to be the length of the garage, but contracted. And now we can think about the events as they play out in this space-time diagram. So we already talked about the event A. What about the event C? What is that? That's where the front of the limo begins to enter the front of the garage. That's just going to be where this red line here meets that green line there. So that's pretty straightforward. It's just going to be down there. What else do we have? Event B. What's that? That's where the front of the limo crashes into the back of the garage. What would that look like on this situation? Well, that would look like the front of the limo crashing into, that would be this right here. So that right there is the back of the garage, and that's the front of the limo. I should probably write these on. Let's call this garage. No, that's limo front, isn't it? Limo front. This is limo back. This is garage back, and this is garage front. So that's what we're dealing with. And this is where the limo front crashes into the garage back. So that's where all hell breaks loose. What other events do we have? We have the event where the garage front meets the limo front as well. So that's going to be kind of up here. That's going to be the event D up there somewhere. So where the green line here meets the red line here. So what does that mean in context when the garage front meets the limo front? that's going to be, what is that going to be? That's going to be, I should probably write this on. So, confusing myself. So this is the, what is this? This is the, so this is from the limo perspective, isn't it? So this is the big L naught. Have I got things the wrong way around? Let's have a look. I was calling garage big L naught. This is the garage perspective, isn't it? So, sorry, I'm confusing myself. This is the garage back. That red line there. This is the garage front. Okay. This is the limo front, and this is the limo back. Like that. Well, sorry, limo back and limo front, isn't it? Limo front, as I was calling it. No, limo back. The rear of the limo and the front of the limo. Yeah. Oh, it's difficult to imagine this. And then I got these the wrong way around, didn't I? So that would be the limo. That'd be the garage. So that'd be the limo. And I was calling that the front, so that's the front of the limo there. That's front. This right here is the garage back. Garage back. The back of the garage. This right here is the back of the limo. Limo back. And this right here is the garage front. So the front of the garage. So this is the limo perspective, where the weld line of the limo is constant, and this is the garage perspective. Okay, yeah. Just take some time to get this right. If you don't, things are going to go haywire. So where the limo back meets the garage back, that's going to be, well, where that green line there, the limo back meets the garage back, so that's going to be the event D. So where that red line meets that green line is where that green line meets that red line. The event B, that's when the garage back meets the limo front, so that's when it starts to crash, and that's right here. Okay, so you can see, as I've drawn it here, you can see how the event B is preceding the event A. What does that mean? It means what does it mean? Well, it means the front. It means the front of the limo is meeting the back of the garage before the back of the limo gets into the garage front. So you can see, as I've drawn it here, the limo would never be completely contained within the garage at one particular instant in time, because the event B precedes the event A. But over here, it would be the case that there is a time where the limo is simultaneously within the garage, and this might seem very counterintuitive, but again, it comes down to the simultaneity of events. And in this problem, it's focusing on the events A and B. That's the most important things. And in this frame of reference, the event A is preceding the event B, but in this frame of reference, the event B is preceding the event A. Now, that can only happen if A and B are connected via what's sometimes called are they called space-like events? Yeah, I think they call it space-like events. So that can only happen when the light cone of B, when the light cone of A is not, B is not within the light cone of A. So you can imagine, and I'll talk about this a bit more in another video, but just for perspective, the light cone from that point is all of the events that can happen in here. So all that basically means is if there's some event here, then that event could be the causation of any kind of event within here. And I think they call these events time-like, because there's more time than there is space. And likewise, and you can take it to the negative here as well. So all of these events are considered time-like with respect to that event. So any event here could be the causation of that event, and any event here could be caused by that event. But all the events here and all the events here, well, they can't be the causations of each other. So if this is the event, let's call it the event A, and this is the event B, then there's absolutely no way that A could cause B, because if A was to cause B, then there must be some kind of information which travels faster than the speed of light. You'd have to have a world line which is traveling like that, and that's actually traveling faster than the speed of light, and that's not allowed. So for that reason, A cannot be the cause of B, and vice versa, B cannot be the cause of A, and therefore, these two events, the simultaneity of them can be flipped around with the right change of coordinates, with the right, with enough speed. You can flip the simultaneity of these events around, and that's what's happening here as I've drawn the situation. As I've drawn it, the event B is preceded in this frame reference, but not preceded in this frame reference. So the simultaneity is flipped around, and that means the events of A and B are separated via I guess you could call it a space-like infill. So there's more space than there is time. What does that mean? Let's try and give that some perspective to the problem here. It means, so if we look at the garage perspective, B has a distance of L naught, and that would be at a time, well, that L naught would be longer than the time. So the coordinate of B here, the x is L naught, but the time t would actually be greater than the L naught for that particular coordinate. So that means, what does that mean? It means if you were to fire a ray of light when the limo back hits the garage front, so that's when the limo is completely contained in the garage. If you were to fire a ray of light when the limo back hits the garage front, then there's no way it could travel a distance of L naught before event B happens. So you could imagine firing a ray of light when the back of the limo reaches the front of the garage to tell the limo to stop, perhaps. But by the time it gets to the front of the limo, it's going to be too late. There's absolutely no way you can tell the front of the limo that the back of the limo is in the garage quick enough so that it stops the limo before it hits the back of the garage. That's pretty much what we're saying here. In this context, that's what that's what I'm trying to get at. So this won't always be the case, obviously, but it depends on how the L naught. It depends on the speed v, and it depends on how L relates to, well, how little L naught relates to big L naught as well. So there's three kind of arbitrary parameters here at play. There's v, there's L naught, and there's big L naught. And depending on those, if the v was larger, then you're more likely to have this situation. But if the big L naught was much larger, then maybe not. I might investigate the maths of this in another video, but I think that's long enough for one video at the moment. And this is I think it's a fantastic insight into the way special relativity works and how the simultaneity of events is so important and so weird. Right? This is completely different to the way most people think about the world. And I think space-time diagrams are just a fantastic way of illustrating how this works. So, okay, so in this video, I'm going to talk about the transformations of the events A and B a bit more, and some of the conditions that might be required on the lengths L0 and little L0, and also the speed v, such that we can attain this situation from this situation, so that we can attain a frame of reference where B precedes A. So let's remind ourselves of the Lorentz transformations. They were this, so they were x prime equals, so it's the Galilean distance x minus vt, and then times by the gamma. And likewise, we had the t prime is the t, and then minus the vx, and then times by the gamma as well. So that's the Lorentz transformation. And I'm just going to focus on the event B, really, and in particular its coordinates. So the event B in the unprimed frame of references, well, it has x equal L0. Let's get that down. X equal L0, and it has so that's the proper distance of the garage. So the length of the garage in its frame of rest, and the time of the point B. Well, I hadn't actually. I don't think I figured that one out yet, have I? Okay, so let's go ahead and figure out the time t, and we can do that just using a bit of straight line geometry. We don't need any weird transformations to do that. You just say this is the red line, x equal L0. So that's the world line of the back of the garage. And the world line of the front of the limo is this x equal vt plus the little l, so the contracted length, x equal vt plus the contracted length little l of the limo. So and we're just going to solve these. I want to do things in terms of L0, big L0 and V. That's what I do want to do things in terms. So I'm going to swap out this little l as remember that's the contracted length. So that's actually just the proper length divided by gamma. So that's the contracted length of the limo. And I'm now just going to simultaneously solve these to find the time coordinate t. So that's fairly straightforward. You set them equal to each other. What colour should we use? So big L0 equals the Vt plus the little L0 divide gamma. And that's dead easy to solve. So you minus that one over there, and then divide through by the V. So you get L0 minus little L0 on gamma, and then divide by the big V. And that's going to be equal to the t. A bit of tidying can be done there. I guess we can times the top and the bottom by gamma, perhaps. Is that going to be a nice thing to do? Let's go ahead and do that. So you get this minus divided by the v gamma. I don't know if that's a nice thing to do, but there it is. So t, the time of the coordinate b is given by that. So t equals gamma L0 minus little L0 divided by gamma v. All right, so now what I'm going to do, I'm going to conduct a transformation on this coordinate which was the coordinates of b in the unprime. So let's get rid of all this working a sec. It's the beauty of video, you can just delete things. And I'm now going to transform. So I'm going to find the x prime. X prime equals the gamma, and then the x minus the vt. So it's going to be this, the L0, and then minus the. Well, we could probably figure this one out just by looking at the geometry of the lines again. Yeah, yeah, this should just be equal to the little L naught. That's going to be the proper length of the limo in so the length of the limo in its frame of reference where it's considered at rest. So, but let's just double check that that's what we're going to get. So we get the gamma times so x is big L naught and then minus v, and then times by the little t is going to be this lot here. So you get gamma L naught minus little L naught, and then divided by the gamma v. V's are going to cancel here. Close that off, and then you can go ahead and expand this out. And what are we going to get? Well, you're going to get things like the gamma L naught, and the gamma L naught is going to cancel here because that's being divided by gamma. So, well, let's just write it out. So you get the gamma L naught minus then gamma L naught over gamma. The gamma cancels, and there's another gamma. So gamma times gamma gives you the gamma squared, and then you have one of the gammas being cancelled, so squared becomes just power 1. So that gives you gamma L naught, and these two terms, this gamma L naught is going to cancel that term, so gamma L naught cancels, and then you get minus minus, gives you a plus, and then again the gammas are kind of cancel, gamma cancels, then you get the little L naught. So that's a very good sanity check. It's just exactly what we'd expect when you conduct the Lorentz transformation. So all is well. And then T prime is, well, this is the one I want to focus on. So this is the time coordinate of event 3 in the prime frame of reference. And this is going to tell you whether simultaneity can be flipped around or not. So this is the interesting one. Let's go ahead and figure this out. So T prime is going to be the gamma, and then times by the T minus Vx. So that's going to be, what's T? The T is that thing. So gamma L naught minus little L naught divided by gamma V. And then that's going to be minus the Vx. So that's going to be minus V and then times by the big L naught. And let's just do a bit of tidying on that again. So the gamma is going to cancel the gamma in the bottom there. So you can write this as gamma L naught minus little L naught divided by the V, and then minus the V gamma L naught. And I want to do a bit more tidying there. What can we do here? What can we do? Do I want to factor the V? It's nice. I guess, well, yes, try and write this as a, so if I times that by V on the top and the bottom, it's going to be the same denominator. And then you have the V squared times the gamma. Can that be tidied up a bit? Well, let's have a look. So you get L naught, and then as a factor you get the gamma minus V squared gamma in front of the L naught, and then the big L naught, and then minus the little L naught, and that's all being divided by the V here. So I'm sure this factor here can be tidied up a bit. Oh, and I may as well factor the gamma there as well, actually. Yeah, it can be factored, can it? So 1 minus V squared times the gamma. That's going to be something nice. Let's just check what it is. So you get 1 minus V squared, and then the gamma is divided by the square root of 1 minus V squared. That's what the gamma is. It's just 1 over the square root of 1 minus V squared. So you can see how this just gives you the square root of 1 minus V squared. So we can rewrite that. I'm running out of space. Let me just continue up here. It's going to be T prime equals, it's going to be that thing, which is now just that times L naught. So we could write that as L naught and then divided by gamma, because when you divide by gamma, it's the same as timesing by the root of 1 minus V squared, and then minus the little L naught, and then I'm going to divide all of that by the little v, like that. So that would be the time of the coordinate b in the prime reference frame. So let's do a few more sanity checks just to check that works. So that's the 3 and the 3 over here as well. Okay, let's do a few sanity checks then. So, well, that's the time of coordinate b in this reference frame. So that would be this time here. Can we calculate that time? Yeah, I think we can. So it would be this world line here is moving at speed v. So the gradient of that line should be, well, the equation of that line would be, what's it going to be? It's going to be related to the big L here, isn't it? So the equation of that line would be x prime thinking. Oh, different ways to think about this. X prime is going to be equal to the big R, and then minus t prime, and the v is going to creep in there somewhere. How is it going to creep in? That's a distance. That's a time. So yeah, you want the v to be there. Yeah, L minus vt prime. So that'd be the equation of this line here. L minus vt prime. So by this at the coordinate b, you know the x prime is little L naught. So you can say the x prime there is the little L naught. So little L naught is the x prime. That's the proper distance of the limo, and that's going to be equal to the big L. That's the contracted length of the garage, and then minus the v t prime, where t prime is the time of the coordinate b, and you can see how that's going to give us the same result. So t prime would be equal to the little L naught, well, the big L minus the little L naught, and then divided by the big B. So that's the coordinate B there. And that agrees with the result we had over here just by using the Lorentz transformation, except this L naught over gamma is the contracted length. So this is all self-consistent, and you can see there's different ways of doing the same thing, which is great, right? It gives you a good sanity check, and it gives you two different perspectives on the same problem. I think the space-time diagram is a much nicer thing to look at, because we're naturally visual thinkers, and it just helps make the situation make sense, much more sense of the situation than what a whole bunch of equations would do. When I first started learning relativity, I would write down pages and pages of this like this, and I would just confuse the hell out of myself, to be honest. And I was using units where the where the speed of light is c as opposed to just 1, and that makes the equations even more tedious. So space-time diagrams and using units where speed of light is 1 makes this a heck of a lot easier to think about. And you can see, if you look at that, the equation for the t prime here, that's going to be, it could be positive or it could be negative. It depends on the sign of the numerator here. So if this numerator is going to be positive, then that would necessarily mean the event B is a time-like with respect to A. So let's draw that out and think about that a bit more. So we had the t prime, the time coordinate of B in the prime frame was the L naught on gamma. So that's the contracted length of the garage, was it? And then minus the L naught, the proper length of the limo, and then divided by the V. And I'm only interested in whether this is positive or negative, because the time coordinate of event A is, well, it's just t equals t prime equals 0. So if B is negative, it's going to precede A, and if B is positive, the time of B is positive, then A is going to precede B. So let's think about that situation. So if A and B are time-like, I'm pretty sure they're called time-like. I might have to look that up in a second. But so that when there's, again, back to the light cone, if there's more time than there is space, then it makes sense to call it time-like. I'm pretty sure that's the convention and the way they've got it around. If it's the other way around, then it's very confusing. I'm pretty sure it's that way around. If there's more time than space, then we call it a time-like interval. So if A and B are time-like, then that would mean the A could necessarily be the causation of B. So that means there could be a world line traveling from A to B, which is slower than the speed of light. And that's going to be the case where T prime would necessarily be positive all the time. And that would mean, for my parameters here, this is what I'm wanted to get to. It would mean the L naught over gamma minus little L naught. That would have to be always greater than 0. So let's think about what that means for this. Well, we can now write the gamma in terms of V. That's going to be root 1 minus V squared, square root. And then you get that times by the big L naught and then minus the little L naught. Like that, and that's greater than 0. And I think I want to write that in terms of V. Let's see if we can do that. So let's go ahead and add that and then divide. So you get this funny 1 minus V squared square root. That would have to be greater than the little L naught divided by the big L naught. Isn't that a lovely expression? And all this stuff is positive, so it's perfectly fine to square here without worrying about the signs. So you get 1 minus V squared. And that's going to be greater than the L naught on big L naught squared. And then from both sides of this, you can just do 1 minus both sides. So, and when you do 1 minus both sides, you have to flip the sign here because you're doing minus one side. And this would be 1 minus little L naught on big L naught squared. And then finally we get the condition if you take the square root. And again, everything's just positive here, so I'm not too fast. V would necessarily have to be less than the square root of this quantity for the events to be considered time-like. So there we go. L naught, little L naught on big L naught. So as like I was saying, you know, if you make V fast enough, then the events A and B become space-like, and they become space-like as soon as V equals or exceeds this. That's the point where the event A can no longer be the causation of B, and that's the point where A and B, the simultaneity can be flipped around. But if V is less than this quantity, then the events are always going to be, time-like, no matter how, so long as the reference frame, in this context, so long as the limo moves slower than this speed here. And, you can calculate what that speed would be. Maybe let's just put some numbers in here just for fun. So if I say L naught, what was that? That was the oh my god, what was that? That was L naught. I forgot it. I have a bad memory. Let's go back again. Little L naught was the proper length of the car. So what is that? That's, I don't know, 4 meters or something like that, perhaps. In the garage, and let's call it big L naught. That could be, say, 6 meters, something like that. And yeah. And this ratio, I mean, I'm not using, and this ratio here, little L naught divided big L naught, well, that would just be 2/3. And you get 1 minus 2/3, and then square root. And that would be just root third for the speed, the critical speed of V. That's the, remember. So what I'm saying now is the speed of your limo would have to be would have to exceed root 1/3 the speed of light in order for the events A and B to the simultaneity to flip around. So that's the takeaway here, and that this is pretty fast, even just for this relatively short distance. So yeah, I think that's pretty interesting, and I had loads of fun. Putting this together. I hope you got something out of it. I wasn't expecting to spend the odd 40-50 minutes talking about this, but there you go. it's just such an interesting problem, and I think we've rinsed it for just about everything it's worth now. So yeah, I will see you in the next one. Okay, so I wanted to do one final video with Desmos just to illustrate how all the variables play off one another, because I think it's a fascinating situation to look at. So what I've gone ahead and done, I've plotted this situation in Desmos, and I've got the parameters L0, big L0, little L0, and the speed v. So remember, little L0 is the proper distance of the limo, and big L0 is the proper distance of the garage. And this frame reference is moving at speed v towards the right with respect to that one. So you go ahead and put this in Desmos, and you can see how all the numbers kind of play off one another. So what I've drawn here, the two green lines represent, well, that's the x prime axes. That's where t prime equals 0. So that's the axes where the events are considered simultaneous with respect to the limo's frame of reference. So here I've got the garage to be a length of 6, just like I considered in the previous video, and that's so that weld line there is, you know, the back of the garage, and this weld line here is the front of the garage. This weld line here is the front of the limo, and this weld line here is the back of the limo. And this just so happens to be the t prime axis as well, so that's where x prime equals 0, and this happens to be the x prime axis, that's where t prime equals 0. And this coordinate b, that's the one I was focusing on so much. That's where the front of the limo hits the back of the garage. So at the moment I've got the speed at 0.3, and well, as it stands, you can see there is some insight to be gauged from the distances here. This axis here is the x-axis, and that's the line of simultaneity in the space-time diagram. That's every space-time event along the axis would be considered simultaneous with respect to in the garage's reference frame. But in the limo's reference frame, every event along this green line is considered simultaneous. So when you measure the length of the limo the distance from there to there would be the contracted length of the limo. So because we're observing the limo moving in the garage's reference frame, so this 3.186 would be the contracted length of the limo. And that's just this L0, which is 4, and then divided by this factor of g. That's what I was calling gamma, but they don't have gamma in Desmos, I'm just calling it g. So when you do the L0 divided by the gamma, you get the contracted distance of the limo, and that just so happens to be 3.186. But when you measure the length of the limo in the limo's frame of reference, well, the length is not quite going to be the same. It's actually going to be the distance from there to there. So this is the x prime axis, and so t prime equals 0, and the value of x prime right there would be the length of the limo. Is that right? Yeah. What would x prime be? That's the value of x prime there would be the length of the limo, and that the x prime value there would just be 4 for that particular space-time event. You can't see it on here, but yeah. So I guess the key point in this question is, when you say the limo is contained within the garage, in the garage's frame of reference, what you're saying is you have this space-time event and this space-time event, and they're both kind of within the blue interval here at the same time. And you can certainly see that because in this situation, well, this point and this point are at the same t equals 0, so they're considered simultaneous, and that's just the contracted length of the limo. So the limo does indeed get contained within the garage at the moment within this frame of reference, and therefore the event A precedes the event B. So let's look at this from the perspective of the limo. I've gone ahead and done that as well here. Here's the limo's frame of reference. So garage, and then over to the limo here. So things have changed a little bit. You can see how the garage length is no longer just 6, it's actually 5.724, because the length of the garage is contracted by that factor of gamma. So this is the distance of 6 and then divided by the g, so it's that length there. This is the rear of the garage, this is the front of the garage, and this is the limo. So you can now imagine the garage kind of moving towards us. And the event B is actually this event here in this space-time diagram. That's where the back of the garage hits the front of the limo, and you can see at the moment the t prime would be positive here. So the t prime here is 5.745 in the limo's frame of reference. So t prime equals 5.745. So it's positive. But observe very closely what happens when I slowly increase the v. So if I slowly pull this up here, you can see how the world lines kind of rotate a little bit. So this is the t-axis, and this is the x-axis in this situation. This is the x prime axis, this is the t prime axis. And as I increase v very slowly, the whole system kind of rotates. It gets lots more squashed, and now you can see that event B precedes the event A. So the back of the garage, is that one, and the front of the limo actually come into contact before the rear of the limo and the back of the garage are before the rear of the limo passes the back of the garage. So the simultaneity has been broken, and you can see that happens when you increase the v. So here's the events being time-like, and here's the events being space-like. Yeah, so and the critical point where this changes, remember, what was it? Let's go back to the maths here. That was at the root 1/3 of the c. So let's take a look at that just as a special example. So it's 1/√3, lots of c. That was the breaking point here. So let's look at that from the garage perspective. Here's the point B, and what we're saying is the distance in the what are we saying? We're saying if V was to go slightly greater, then the limo would change. Let's have a look. I made a mistake in the maths. Okay, so this was squared, wasn't it? So this would be 2/3 squared. So that would give you -4/9. So this would be the root of 5/9. That's going to be the critical point where these simultaneous flipped around. So this would be root 5/9 of c. I made a mistake. Okay. So let's go back. Let's see if that works. It's going to be the square root of 5/9. So square root 5/9. Okay, there we go. That's what I'm looking for. So if we go back to the garage frame of reference, you can see how the event B is actually coincident with, for that particular value of B, the event B is actually coincident with the x prime axes. So what that necessarily means is in the limos frame of reference, both the back and the front of the limo hit the garage. So this is what is this? This is the front of the limo and this is the back of the garage. So the front of the limo hits the back of the garage at exactly the same t prime when the rear of the limo hits the front of the garage. So, and those events are simultaneous in the limo's reference frame. If we go back to the garage reference frame, you can see that's the line of simultaneity here, and you can see those events are lying along that line of simultaneity. So the event A and the event B are considered simultaneous in the limo's frame of reference. But you can clearly see they're not simultaneous in the garage's frame of reference. If I was to go slightly faster here, then in the limo's frame of reference, this event B is going to precede the event A. If I was to go slightly slower, the event A would precede the event B. So that's what the mouse is telling us, and I think